In this video we are going to look at writing vector equations for lines, converting vector equations into both parametric equations and then also into Cartesian equations. And then lastly we're going to find the angle between two lines that are in vector form. Two physical lines, not just two vectors. So to start, we're going to be looking at lines and planes in space. So think about you're sailing a ship in the ocean at noon, you're at point -2, you're traveling at a constant rate, 5 nautical miles per hour on the vector, 3i plus 4j. So keeping in mind that unit vector form, the I part is representing your x and then the j part is representing the y. So we need to figure out what the coordinates are at each of the times. So this again started at noon, so 1 hour later we went from -2, over to 1,5. And then at 7, when you go 7 hours later, you started at -2, and then you moved 3 for every hour, so 3 times 7. And so that's going to be the new x value, which is 19. And then your y value, the y location, you started at 1, and then it's 4 for your y times 7 hours later, which gives you 29. So it's the coordinate point 1929. At 11 a.m., we had to go through our process. Sorry, that's supposed to be 11 p.m. There we go. So at 11 p.m., it's that -2 plus 3 times 11 hours. And then for your y, it's 1 plus 4 times the 11 hours, which gives you your location of 31 and comma 45. 3 a.m. is 15 hours later, which gives you the coordinate point 43, 61. T hours later, therefore, I take my x value, which is -2, and then I add t times 3, or 3t, either way you want to think about it. And your y value started at 1 plus t times your y value is 4. What we just wrote here is actually a parametric equation because it's my x and y value both in terms of a third variable, t. Now I can also represent this in vector form. So I'm going to do both of these, but now I'm going to go into my vector form. My vector equation for this, I had this starting point, which was -2, 1. So that's where I started. And I'm adding that unit vector form. The 3 again is your x, the 4 is the y, and that's multiplied by some t value. And the end result is going to be your xy coordinate. So I left some space. So that's your vector equation. And once you have your vector equation, you can very quickly move into your parametric equation, which is what we actually came up with before. My x equals -2 plus t times 3, and my y equals 1 plus t times 4, or 4t, either way you want to do that. If I want to do my Cartesian equation only has x's and y's, no t's. I'm going to have to get my t out of there. If I want my Cartesian equation, it's usually y equals form. So take that initial x equals equation, x equals -2 plus, oops, that's a plus, 3t, solve it for t. That's what t equals. Now that I know what t equals, I'm going to substitute this in. It's my y equation for t. And it's going to, in essence, put this into slope-intercept form for me. So therefore, y equals x plus 2 over 3, multiply that by 4, plus 1. So if I want to go through, simplify this out, I get y equals 4/3 x plus 8/3 plus 1. which is y equals 4/3 x plus 11/3. So there's my slope-intercept form. Make a mental note. Here's your slope. Here's your vector. Those are two very important pieces. Yes, they are flipped around because your x's are on top, the y's are on the bottom. The only other thing that we should also denote here is that our x value has to be greater than or equal to -2. Only reason we have to say that is because my time that we're looking at has to be greater than or equal to 0. If I go back to this problem, what the actual problem starts off by saying is we're in the ocean, we're looking at noon, this is where we started, and then we've continued to travel from there. So therefore my lowest x value that I can have is a -2. That's the starting point. You're controlling your domain piece there. Okay, good. This 3, 4, as I talked about, is a vector. That's actually your velocity vector. Keep running out of space. That's what that is. That's our velocity vector. So if we are looking at 2 dimensions and 3-dimensional lines, we can look at, in 2 dimensions, the slope, the direction, based on a fixed point. So we'll start by looking at the 2-dimensional ones, and then we'll kind of look a little bit more 3-dimensionally. So here's my situation. I'm starting at the origin O. So the vector from O to R equals the vector from O to A plus the vector from A to R. So therefore, I'm going to call this vector OR, I'm going to call that vector R. So then I know vector R is just vector A plus B is my vector direction, and it's multiplied by some number, by some constant. It's that same exact vector, we just have to figure out its length. So that's the equation for your line. In 2 dimensions, we have the vector equation, and then, so here's my vector equation. Here's that multiplier on there, because it's going to move it a certain multiplier in length. A sub 1, A sub 2, that's a starting point. That's kind of thought as A sub naught, because time can kind of be thought of as 0. So we can find any point R along this line, any point on that line. A1, A2 is a fixed point. That's kind of that starting point. And then the B1, B2 is the direction vector, which direction it's physically going to go. T again is going to be that multiplier. So B, vector B, is B1, B2. That helps us calculate our slope in 2 dimensions. Because remember, your slope is your rise over your run. That's the one part that you got to be really careful about. The bottom values are your y's. That's your change in y. Your top values are the change in x. So that's your rise over the run. So based on this information, I can write the vector equation in parametric form. X equals A1 plus T times B1, and Y equals A2 plus T times B2. So that we can figure out what our time is. We'll be able to solve these simultaneously to figure out what happens to T along the way. So let's look at an example now. So we want to find the vector of the equation of the line passing through the point A, which is 1, 5, and the direction of 3, 2. We want to find the vector equation, the parametric equation, and the Cartesian equation. So starting with our vector equation, in my opinion that's the easiest one to start with. My vector equation, I'm finding some xy point. that equals your starting point. I'm starting with the point 1, 5. That's that fixed point that we're looking at. It's going through that point, plus t times the direction vector, which is 3, 2. You do need to clarify around these. Most of the time, if we're doing just generics, t can be anything. T can be any real numbers. It's a set of reals. If I'm dealing with story problems, you may have to look at, okay, I can only talk about from a positive time or from a positive aspect of it. If I have my parametric equation, they're going to both be in terms of t. So x equals 1 plus 3t, and y equals 5 plus 2t. If the t portion of it is first, for parametrics, you may want to write it second, just to help you know that this is your velocity vector, especially if you're going from parametric form to vector form. And then lastly, Cartesian form. I'm going to have to solve for my t. Again, I like it y equals. So y equals 5 plus 2 times, now I have to solve for t. So to solve this one for t, it's x minus 1 divided by 3 equals t. So therefore it's 2 times x minus 1 over 3, which if you'd like to write that out, it's y equals 2/3 x minus 2/3 plus 5 plus 4 1/3, if my math is correct. So those are the three different forms of writing your equation. If you're given it in the vector form and parametric form, you can always flip between those two, finally move to Cartesian form. Trying to start in Cartesian form and move up a little bit more difficult because you need that coordinate point to work with. So here's a little bit more of a real-world story problem. We have a particle located at point P, which is x of t, y of t, because they both depend on t, moving such that x of t equals 2 minus 3t and y of t equals 2t plus 4. T has to be in the positive number, or 0, and then the distance is in meters and time is in seconds. So if I want to find my initial position, I'm going to start by setting up my actual vector equation. So I'm going to put xy equals, and then I have my initial, which is not attached to my t, so for my x that's 2, and for my y it's 4. Remember, sometimes those are going to be separate. Let's slide this over. And then my t value times what it's attached to, a -3 and a +2. So there's my vector form. My direction vector is -3, 2. My initial point, when I put 0 in for t, is 2, 4. So that's the initial position of point P. I can write that as a coordinate point as well, so we know exactly where that's at. So then I'm able to plot each of these points. So I have this initial point, 2, 4. So when time is 0, it's at 2, 4. When time is 1, you're plugging a 1 now in for t. When time is 1, it's -1, 6. It's -4. Eight, and then when time is 3, it's -7, 10. So that's the direction it's moving. It starts when t equals 0, and it continues in this left and north direction. So I then can find the speed of this. To find the speed, use your direction vector. Here's my direction vector. The speed, therefore, is the square root of 3 squared plus 4 squared. So the speed, therefore, is the square root of 13 meters per second. So this is dealing with two-dimensional features. Given some parametrics, I like to write them into vector equations, and then I can find my information from there. In three-dimensional lines, my R now is a point. I'm not going to draw this one. It's a little bit harder to see three-dimensionally. And then A A1, A2, A3, that's going to be some fixed point on the line. And then B again is the direction vector. So this is telling us which direction it's going to go. So I can do my parametric equations. Oh, they don't want to pop up. There's two of them. So my x is A1 plus t times B1, y, and then lastly the z is A3 plus B3 times t. And again, t is in the set of reals. That's given your parameter generically, keeping in mind based upon real-world applications, we may not be able to specifically, we may have to go in the positive direction, include 0 as well. There is no gradient for 3D lines. We just say it's a direction vector. Okay, whereas in 2D lines, let's see if I can find that. In 2D lines, that direction vector is that slope, that's the gradient. In three-dimensional lines, that is not the case. So, example. Find the vector equation of the parametric equations and parametric equations of the line through that point and in the direction 4i plus 5j minus 6k. Keep in mind, make sure your unit vector form is in order ijk. Then I can quickly say x, y, z. That any coordinate point, we have the starting point 1, negative 2, 3, plus some multiplier times 4, 5, negative 6. So here's our vector equation. No restriction at this point. T is in the set of reals. The first one, vector equation. Rewriting this into parametric equations, just set up x equals 1 plus 4t, y equals negative 2 plus 5t, z equals 3 plus negative 6t. Okay, we will just be working on vector equations and parametric equations when we're looking at 3 dimensions. So I can find the parametric equations of a line through 2 points. It is a line, remember, it keeps going in both directions. So I'm either going to have to find vector AB or vector BA. For consistency's sake, let's just do AB. So if I'm finding vector AB, it's my B values subtracting my A values. So that vector is negative 3, 1, and then negative 2. So now that I have my velocity vector, I can write my parametric equations. I need to start with a point, either A or B. It's a line. And from that point, I'm going to use my velocity vector multiplied, of course, by that t value. So therefore, my x equals my starting point. So I'm going to use this point initially. 2 minus 3t. Y equals negative 1 plus t. And z equals 4 minus 2t. T is in the set of reals. That's if I use my initial point as A, as my starting point. I could also use B. It's just some point that you're looking at. When you start dealing with story problems, it may be the initial point, but we are looking at lines. So another option could be x equals, using point B, negative 1 minus 3. I have to have a different constants. We'll call that s. Y equals 0 plus s, and z equals 2 minus 2s, where s is in the set of reals. If I want to compare the two back and forth to each other, this is kind of a neat little feature that takes place here. My s value, it equals y, so that's the same thing as negative 1 plus t. Keep doing that with my plus sign. So that's how they relate to one another. These are exactly the same type of situation. Depending on what your multiplier is, you are going to be able to find points on the exact same line, whether you use this black set or you use the red set. You'll get the exact same points on a line. It keeps going in both directions. Next, we're going to focus on the angles between two lines in both 2 dimensions and 3 dimensions. I'm physically looking at the angle between two lines. One line, another line. So I'm looking at the angle between them. If I'm looking at the angle between two lines, I'm going to use the following. The cosine of theta equals vector b dot, b1, sorry, dot vector b2 over the length of vector b1 times the length of vector b2. The last piece we're going to add in here are absolute value bars. Those are absolute value. The reason we're looking at the absolute value is this is going to find my acute angle. If I don't do the absolute value, I may get the obtuse angle, then I have to subtract it from 180, because for consistency's sake, we will always be asking for the acute angle. If we're trying to find an angle in between, we're going to find the acute angle, or if it's perpendicular, but you know how to find the perpendiculars. Remember, their dot product has to equal 0 for them to be perpendicular. Okay, so given some information, I can find the point of intersection if it exists and the angle between the lines. They may not exist. The angle, or the two lines, especially when we start looking at 3 dimensions, may not cross, and you're going to see more on that in another video. But if it doesn't exist, you can still find the angle, which again we'll talk about a little bit later, but the intersection is not going to be a true statement. So I've got the following two lines, L1, L2. These are my vector equations. So if I want to find, first let's just find the angle between them. I just gave you guys that formula. So if I want to find the angle between them, I have to do the dot product, and the dot product involves the velocity vector. So I'm using those two vectors, -3, 1, -2, and 2, 4, 1. I'm going to do the cross product, dot product, excuse me. So the cosine of theta equals the absolute value of -3 times 2 plus 1 times 4 plus -2 times 1 all over the length of each of them. So the square root of 9 plus 1 plus 4 is 14 times 4 plus 16 plus 1, square root of that is square root of 21. Therefore, on the top, the cosine of theta equals 4 over the square root of 294. If I do cosine inverse, theta therefore equals 76.5 degrees. So these two equations meet at an acute angle of 76.5 degrees. Now we can find if they actually intersect. This is 3 dimensions. We can figure out what they have to equal if they intersect each other. In order to do that, I'm going to rewrite these into parametrics. I'm going to have them in terms of S and in terms of T, and then I'm going to have to do some elimination to combine them together because I'm going to have multiple variables along the way. I'll actually do substitution. So let's see. I'm going to write my equations into parametric form. My x values are going to equal, so my 1x value is 2 plus -3s. Its y value is -1 plus 1s. And its z value is 4 minus 2s. So I'm just putting these into parametric form for my x, y, and z. I'm trying to find where they intersect, so I'm finding each of the same x, y, and z points. So when I look at the other one, it's 1 plus 2t, and y equals just 4t, and then z equals 2 plus t. So now I'm going to do substitution with these to figure out what my s value is, what my t value is, and then I'm going to solve for those and then check them, make sure it works. If it works, I can find exactly where they crossed. So I'm just going to set 2 of them equal to each other. I only need 2 because there's going to be 2 unknowns. So x equals this, and x equals this. So I set those two this part's equal. So -2 plus -3s has to equal 1 plus 2t. And my other one, I'll do y. -1 plus s equals 4t. So this is my set I'm going to work with. So I'm going to get my s's and t's on the one side, my constants on the other side. So the set I'm actually going to start looking at is negative 3s, subtract the 2t, equals, subtract the 1, negative 1, and then this is an s, minus 4t equals a positive 1. So doing elimination with those, maybe I want the t's to drop out. Multiply the top one by negative 2. So when I do this, I get 6s plus 4t equals 2, and s minus 4t equals 1. Add those up, I get 7s equals 3, so s equals 3/7. Going back up, I have what s equals. I'm going to substitute this, therefore, back into my equations for s, and well, I'm going to have to find t as well. So let's see. We'll use that equation there. So therefore I know negative 1 plus 3/7 has to equal 4t. Therefore, add these two together, I get negative 4s, divide by negative 4, so I get negative 1/7 is what t is. So I found s, I found t. So now I should be able to find my x, my y, and my z. I have my s value, so I can plug that in and find, if I plug that in to those, that's going to give me my x, y, and z. And then I also have my t. So if I take this t value, plug it in for here, they need to give me the exact same values. If they give me the exact same values, that's where they cross at that coordinate point. If they do not give me those exact same values, something else is going to happen. I was able to find s and t, so when I substitute in the 3/7 in for my s values, and I do the multiplication, I don't get the same value when I plug in my negative 1/7 for t. So when I take this negative 1/7 and say I put it in here, z therefore is supposed to be t minus 1/7, which is 1 6/7. When I put s in, which is 3/7, when I put 3/7 in for s, I get z equals 4 minus 2 times 3/7 is 6/7. Provided I did the math right, I get 3 1/7. Those are not equivalent values. Because of this, going back to the problem itself, it says find the point of intersection. There is no point of intersection. These are skew lines. They do not cross. It's saying that they should be different values, which is the reason that these are skew lines. We'll talk a little bit more about this in an upcoming video. It's not the next one, the one after that, as to how we can kind of figure this out a little bit quicker maybe. But this is part of the process. If I don't get the same value, they can't cross the same spot. It's unlikely to occur.